Hello there, and welcome. I am the sleepy astronaut. I'm so glad you found your way here. Maybe you've had a long day, or maybe you just like falling asleep to thoughts about space and the stars. Either way, tonight's journey is for you. Tonight, we will drift together through the quiet dark of the cosmos to explore neutron stars. I have watched these strange remnants of the universe for eons, floating past the wreckage of ancient stellar giants that burned brightly and ended their lives in cataclysmic explosions. What remains behind are shattered cores of unimaginable density, spinning silently like cosmic lighthouses in the void. As we wander through this quiet corner of space together, we will observe these heavy, pulsing mysteries from afar. They are windows into the raw, powerful machinery of a universe I have spent lifetimes traveling through. If you enjoy these calm journeys through space, I invite you to subscribe or leave a thought below. It helps other astronauts find their way here. But for now, your day on Earth has come to an end, and your journey through the stars has begun. You don't need to do anything, just relax and let your body sink. Let your eyes grow heavy and allow your mind to drift into space. Let's begin. To understand a neutron star, we must first look back at the long and turbulent life of the immense titan that birthed it. Long before these dead cores ever began to spin in the cold, silent dark of interstellar space, they were brilliant, blazing giants with initial masses ranging from 8 to upwards of 20 or even 50 times that of our Sun. These massive stars lived fast and burned furiously, dominating their local sectors of space with terrifying luminosity. Their surfaces radiated with a blinding, sapphire-tinted brilliance, and their interiors reached core temperatures exceeding 1 billion Kelvin. Deep within their scorching interiors, a relentless nuclear engine roared night and day, fighting a lifelong, desperate war against gravity. Nuclear fusion worked tirelessly, crushing lighter elements into heavier ones, fusing hydrogen into helium, and releasing staggering amounts of thermal energy to keep the colossal structure from collapsing in upon itself under its own immense weight. Gravity is the great and patient hunter of the cosmos, pulling inward constantly with absolute, unyielding patience to crush a star down to a single mathematical point. For millions of years, the outward thermal pressure generated by nuclear fusion held gravity at bay, creating a delicate, trembling balance that kept the giant stable against its own mass. But stars of this magnificent magnitude cannot burn forever. They consume their precious fuel at an astonishing, reckless rate, devouring hydrogen in their cores at a breathtaking pace to feed their gargantuan appetites. Once the hydrogen fuel in the core is completely exhausted, the core contracts, heating up further through gravitational compaction, until it becomes intensely hot enough to ignite helium fusion, transforming 3 helium atoms into a single carbon atom through the delicate physics of the triple alpha process, providing a temporary reprieve from the crushing dark while continuing the relentless cycle of consumption. This cycle repeats through successive, increasingly rapid stages as the star ages and evolves over millions of years. The star burns carbon, then neon, then oxygen, and finally silicon, building a complex, layered structure like an onion made of nuclear fuel, where heavier elements sink toward the center, while lighter burning shells surround them in a chaotic symphony of thermodynamics and convective currents. Each new stage burns faster than the last, flashing by in a mere few years for carbon, months for neon and oxygen, and collapsing into days or even hours when it reaches the final silicon burning phase. Throughout all of this frantic activity, the core fights for survival, maintaining the thermal pressure needed to keep the outer stellar envelope inflated into a colossal red supergiant that spans distances greater than the orbit of Jupiter. But this desperate balancing act has a strict physical limit written deep into the fundamental laws of nature. That limit is iron. Iron is the ultimate death knell of a massive star. Unlike every lighter element that came before it in the stellar furnace, fusing iron does not release energy. It absorbs it. Iron possesses one of the highest nuclear binding energies per nucleon, meaning it represents a thermodynamic dead end, where no further energy can be extracted through fusion. The moment the core turns to iron, the internal engine catastrophically fails because there is no more fuel left to burn that can yield an energy profit. The outward pressure vanishes in a fraction of an instant, and gravity wins the war in the span of a single second, shattering the delicate balance that had held for millions of years. Imagine an iron core roughly the size of the planet Earth, weighing more than our entire sun, collapsing inward at a quarter of the speed of light. It crashes down toward the center with an unimaginable kinetic fury, tearing through the layers above it. As the infalling material slams violently into the dense, incompressible core at the center, it can go no further and rebounds in a cataclysmic explosion known as a core collapse supernova. In this violent final gasp, 99% of the total gravitational binding energy escapes in a blinding, ghostly flood of neutrinos that stream straight through the star's outer layers, while the resulting shockwave blasts the rest of the material into the galaxy at thousands of kilometers per second. Gold, platinum, iron, the very atoms that make up rings on fingers, deep oceans, and human blood, are violently forged in the chaotic heart of the explosion and scattered across the dark void. Yet, amidst the blinding flash and the expanding shockwave, something far stranger happens at the very center of the ruin. The outer layers are blown out into the great cosmic ocean forever, but the core itself is trapped by its own staggering mass. Squeezed by a force beyond human comprehension, protons and electrons are crushed together through electron capture, forced to merge into pure neutrons while shedding neutrinos into the abyss. The empty space inside the atomic architecture is completely erased, stripped away by the unrelenting weight until matter can compress no further. At this nuclear saturation density, degenerate neutron pressure halts the collapse completely, creating a tightly bound sphere of pure nuclear fluid. This newborn remnant radiates intense heat and magnetic energy into the expanding shell of debris, casting a dim, ethereal glow upon the receding gas clouds as they drift further away into the interstellar medium. Over countless millennia, as the shockwave dissipates into the vast expanses of space, the core settles into its eternal configuration, cooling slowly through neutrino emission and photon radiation from its crystalline crust. What remains behind in the smoking ruins is a naked, shivering sphere of pure nuclear material, measuring only about 20 kilometers across. As we float here in the quiet aftermath of that ancient explosion, watching the debris slowly fade into the velvet black, we can look upon the silent survivor. It does not glow with the fierce, roaring fire of its youth. It is small, dark, and unimaginably heavy, holding the mass of a star inside the dimensions of a small city. The giant is gone, but the remnant remains, waiting quietly in the dark. When you look upon a neutron star from the safety of the void, you are immediately struck by a profound optical illusion, because nothing in our everyday terrestrial experience prepares us for something so physically small, yet so overwhelmingly massive. A typical neutron star spans only about 20 kilometers across, meaning you could drop it right into the middle of a metropolitan city, and its outer edges would barely graze the distant suburbs, or you could submerge it in Lake Michigan, and it would sink straight through the water, plummeting through the sediment, until it rested heavily on the deep bedrock far below. Yet, within that tiny, unassuming sphere lies a stellar mass greater than 1.5 to 2 times that of our Sun, squeezed down until every single scrap of atomic empty space has been entirely and mercilessly erased by the relentless force of gravity. To truly grasp this mind-numbing density, you have to leave behind the familiar rules of the everyday world and look deep into the microscopic architecture of matter. In normal matter, the kind that makes up your physical body, the air you breathe, and the solid planets beneath your feet, atoms are almost entirely empty space, with electrons orbiting atomic nuclei at vast relative distances. If you were to take away all the void surrounding the nucleus and electrons of every single atom in a human body, you could fit all 8 billion people on Earth into a space the size of a single sugar cube. Now, take that atomic architecture and scale it up to the absolute physical limit under extreme gravitational pressure. In the heart of a neutron star, gravity has exerted a pressure so absolute that it has crushed the orbiting electrons straight into the protons, forcing them to undergo electron capture and merge together into an unbroken solid sea of neutrons. The result of this extreme compression is a material of unimaginable density, reaching nuclear saturation densities where a single teaspoon of this nuclear soup would weigh roughly 6 billion tons on Earth. If you were to bring even a microscopic speck of this star into our terrestrial atmosphere, it would instantly plummet straight through your floor, right through the heavy concrete foundation, and keep burrowing all the way down toward the center of the planet, tearing through rock and steel as if they were made of morning mist. It is matter in its most stubborn, degenerate state, holding the line against total gravitational collapse only by the sheer quantum pressure of neutrons pushing back against one another. Yet for all its crushing heaviness and alien physics, the outer surface of a neutron star has a surprisingly structured and rigid landscape. As we drift closer through the dark, you can see a remarkably smooth crust made of iron nuclei locked into a rigid, crystalline lattice, held together by gravitational and electromagnetic forces so intense they defy standard human imagination. This metallic crust is as hard as diamond, yet it is only a kilometer or so thick, acting as a brittle shell resting over the turbulent depths below. The intense magnetic fields and extreme gravity warp the atomic nuclei in this crust into complex, elongated shapes known as nuclear pasta, where matter forms interwoven rods and flat plates before transitioning entirely into the uniform soup of the interior. Walking or standing upon this crust is entirely impossible, not only because of the sheer physical architecture, but because the local environment enforces a brutal, unyielding control over anything that dares approach its domain. Beneath this thin, rigid metallic shell lies one of the strangest and most exotic states of matter in the entire universe. An ocean of superfluid neutrons and superconducting protons. In this hidden depth, cooled by time yet still maintaining immense thermal energy at its core, the neutrons flow without any viscosity or friction at all. They endlessly slide past one another in a silent, perpetual current, never slowing down, never losing kinetic energy to thermal resistance, and creating macroscopic quantum phenomena on a grand stellar scale. Vortices of quantum fluid swirl through the interior, spinning at rates independent of the solid crust, which leads to sudden internal adjustments known as starquakes, when the crust and the inner superfluid drift out of alignment. It is a frictionless liquid sea trapped inside a prison of pure, unadulterated gravity, quietly operating according to the laws of quantum mechanics while wrapped in the dead husk of a massive star. And then, of course, there is the gravity itself, which defines the absolute boundaries of existence around this dense object and warps the fabric of space-time itself. If you were to step off our observation craft and onto the surface of this neutron star, the gravitational pull would be roughly 200 billion times stronger than the pull you feel beneath your feet right now. The escape velocity reaches a staggering half the speed of light, meaning light itself bends noticeably as it travels around the severe curvature of the star. A single feather, dropped from a height of 1 meter, would not flutter gently downward. It would hit the metallic ground in a microsecond, slamming into the crust with the kinetic energy of a falling car. Your own biological body would be instantly flattened, sheared apart by extreme tidal forces, and smeared across the surface as a microscopic, ultra-thin layer of atomic dust, forever pinned to the dense core by forces you could never hope to resist. As we hover just above this crushing landscape, the sheer scale of the physics at play is enough to make your mind spin, balancing absolute stillness with terrifying subterranean power. But the star itself does not just sit still in the quiet dark. It rotates, spinning with a frantic energy that wakes up the surrounding space in ways that few things in the universe ever can, preparing to cast its invisible power across the cosmic void. As we watch this tiny sphere of compressed matter spin in the velvet dark, another invisible and violent force awakens around it, born directly from the fundamental physics of stellar collapse. When a massive progenitor star undergoes core collapse, it takes its original ambient magnetic field with it down into the abyss. Through a crucial physical principle known as magnetic flux conservation, as the core shrinks from a sprawling diameter of millions of kilometers down to a mere 20 kilometers, the magnetic field lines are squeezed, concentrated, and compressed into an impossibly tight space. The total magnetic flux passing through the stellar cross-section remains constant, meaning that as the surface area plummets by billions of factors, the magnetic field density skyrockets exponentially. The result is a magnetic field of unimaginable fury, with surface strengths regularly reaching 1 trillion Gauss or more, trillions of times stronger than anything we can generate in our most advanced laboratories on Earth. This titanic magnetic storm twists, crackles, and saturates the space around the dead star. Invisible to the naked human eye, but howling with high-energy radiation across the entire electromagnetic spectrum, transforming the quiet void into a roaring arena of magnetic pressure. At the very same time, as the massive star collapsed, it had to spin faster and faster to conserve its total angular momentum, operating on the exact same physical principle as a figure skater pulling their arms inward during a rapid pirouette. A giant star that once took weeks or even months to complete a single sluggish rotation now whirls around its axis with terrifying speed, completing dozens or sometimes hundreds of full rotations every single second. The equator of this tiny stellar corpse bulges outward under the immense centrifugal strain, while the entire object becomes a high-speed dynamo spinning through the cosmic void, carrying its colossal magnetic field along with it in a relentless, blurring dance that defies everyday intuition. The conservation of angular momentum ensures that the rotational kinetic energy stored within this tiny core is staggering, providing an engine that can power the surrounding phenomena for millions of years. This combination of frantic rotation and hyper-dense magnetic fields creates a powerful, dynamic magnetosphere that fills the space immediately surrounding the neutron star, acting as an accelerator of subatomic particles. Within this turbulent zone, the rapidly changing magnetic fields induce staggering electric potentials, generating electrical fields strong enough to rip electrons straight off the metallic crust and accelerate them outward into the void. These charged particles are trapped in the fierce magnetic grip and hurled along curved trajectories at nearly the speed of light, undergoing severe relativistic particle acceleration. As these ultra-relativistic electrons and positrons spiral along the open magnetic field lines near the poles, they emit intense beams of synchrotron radiation, channeling vast amounts of electromagnetic energy into narrow, concentrated cones, shooting directly out from the magnetic poles into the surrounding expanse of space. To us, floating at a safe distance in the quiet void of deep space, these brilliant beams sweep across the cosmos like the rotating lamp of a cosmic lighthouse. Because the magnetic poles are misaligned with the physical axis of rotation, the beam does not point steadily at us, but instead cuts across our line of sight with rhythmic, mathematical precision. Every time the sweeping beam flashes past our observation point, we catch a steady, rhythmic pulse of radio waves, X-rays, or gamma rays. Blink, blink, blink. A heartbeat from the dead, echoing through the absolute silence of space for millions of years with metronomic exactness. It is an astronomical clockwork driven by extreme physics, marking the passage of time in the dark ocean of the universe, providing astronomers with one of the most reliable timing mechanisms in existence. Some of these spinning cores possess magnetic fields even more violent, capable of warping the quantum vacuum of space itself. But the standard pulsar offers a soothing, hypnotic regularity as it turns. Yet, despite the invisible violence radiating from their poles and the blazing energy tearing through their magnetospheres, the deep space immediately surrounding our vantage point remains eerily calm. We can sit here in the quiet dark, watching these phantom beams sweep through the distant dust clouds, lulled by their relentless rhythmic pulse as the universe turns slowly around us, carrying us deeper into the tranquil night. While many isolated neutron stars gradually slow down over vast stretches of geological and cosmic time as they bleed their rotational energy away into the surrounding vacuum of space, a special and extraordinary class of these dead cores experiences a dramatic and unexpected second act. These are the millisecond pulsars, the absolute speed demons of the cosmos, which complete a full rotation hundreds of times every single second with mesmerizing regularity. They blur past so fast that their individual, sweeping pulses merge together into a steady, unbroken hum, sounding like a high-pitched harmonic vibration echoing quietly through the cold void. To understand how a dead star can achieve such impossible velocities, we must look away from isolated remnants and focus instead on the complex, intertwined dynamics of stellar partnerships, where gravity creates both destruction and rebirth in the dark expanses of the galaxy. To reach this blistering, hyperspinning velocity, a neutron star usually cannot accomplish the feat on its own, because an isolated remnant naturally loses rotational energy through magnetic braking and particle emission as the eons pass. Instead, nearly all millisecond pulsars are born within binary star systems, locked in a slow, inescapable gravitational waltz with a companion star, which is often an aging red giant or a sun-like star sharing a common center of mass. For millions of years, the two stars orbit each other in a stable cosmic harmony, until the companion star begins to exhaust its own nuclear fuel, swelling outward in size as its outer layers expand and cool. As the companion swells to monstrous proportions, its outer atmospheric layers drift dangerously close to the insatiable, crushing gravitational well of the neutron star, breaching the invisible boundary known as the Roche lobe, where the gravitational pull of the dead core finally overwhelms the grip of the parent star. Once this critical boundary is crossed, the dead core begins to feed on its living partner, initiating a vast and prolonged transfer of stellar material that can last for hundreds of millions of years. Gravitational tides strip glowing streams of hydrogen and helium gas away from the bloated companion star, pulling the matter across the invisible chasm in a continuous cascade of plasma. Because this falling gas carries both mass and rotational momentum, it cannot simply plummet straight down onto the surface of the neutron star, due to the strict physical laws governing the conservation of angular momentum. Instead, the infalling stream flattens out, forming a brilliant, swirling accretion disk that wraps entirely around the equator of furnace-like heat, shining brightly across interstellar distances in high-energy X-rays as the matter prepares for its final descent. Within this turbulent accretion disk, the gas spirals inward over countless millennia, frictionally heating up to extreme temperatures reaching millions of Kelvin that radiate intense X-rays and ultraviolet light into the surrounding space. As every single gram of stolen matter slowly spirals inward and finally settles down onto the rigid iron crust of the neutron star, it transfers its accumulated orbital momentum directly to the core. This continuous injection of matter and motion acts precisely like an invisible, persistent hand pushing a merry-go-round, spinning the ancient dead core faster and faster with each passing millennium. The rotation rate climbs steadily from a sluggish spin into a blistering whirl, transforming the quiet remnant into a hyper-rotator, operating at the absolute structural limits of matter where centrifugal forces threaten to tear the crust apart. Eventually, after feeding for eons, the neutron star reaches its terminal spin velocity, often completing hundreds of rotations every single second, while spinning at a significant fraction of the speed of light. Its equator bulges outward noticeably under the immense centrifugal strain, and its intense magnetic field becomes strangely subdued and buried by the steady, lifelong accumulation of accreted gas, though it remains powerful enough to channel particle beams into the void. As we watch these hyperspinning remnants hum softly in the dark, they feel less like dead stars and more like ancient, immortal engines that have been jump-started back into violent, beautiful action by the grace of gravity. They stand as a magnificent testament to the strange, recycling nature of the cosmos, where even the catastrophic end of a massive star can give way to a furious, brilliant new beginning, lulling us deeper into the tranquil night as we drift past the spinning lights of the galaxy. While standard pulsars hum with a steady, reliable rhythm driven by intense rotation, there exists a rarer and far more violent subclass of dead stars that push the laws of physics to their absolute breaking point: the Magnetars. If a normal neutron star is an extreme object, a magnetar is a terrifying anomaly, possessing magnetic fields so overwhelmingly powerful that they defy normal human comprehension. To understand how these titans of magnetism are born, we must look back to the birth certificate of the supernova itself, where a very specific combination of conditions must align during the final seconds of stellar collapse. When the core of a massive star implodes, it must rotate with astonishing rapidity, completing a full spin every millisecond or two, while maintaining vigorous internal convection currents. This chaotic churn acts as a cosmic dynamo, amplifying the seed magnetic field of the progenitor star through magnetohydrodynamic processes, stretching and winding the magnetic flux lines until they reach densities that stagger the imagination. The resulting magnetic field strength at the surface of a magnetar reaches between 10 to the 14th and 10 to the 15th Gauss, which is 1,000 times stronger than a typical radio pulsar and trillions of times more powerful than the strongest magnetic fields ever generated in laboratories on Earth. To grasp the sheer scale of this invisible power, consider that the energy stored within a magnetar's magnetic field is greater than the total electromagnetic energy output of our Sun over tens of thousands of years. This titanic field permeates not only the solid crust of the star, but extends outward for hundreds of kilometers, creating an intense, suffocating magnetosphere, where the vacuum of space itself is fundamentally altered by the sheer intensity of the forces at play. Within this extreme environment, quantum electrodynamics takes over in ways that seem straight out of science fiction. The magnetic field is so intensely strong that it exceeds the critical quantum limit, causing the very vacuum of empty space to become polarized. Virtual electron-positron pairs, which constantly pop into existence and vanish in the quantum foam, are forced to align with the magnetic field lines, turning the vacuum into a birefringent medium that bends and splits light passing through it. If a human was somehow able to drift within 1,000 kilometers of a magnetar, the magnetic field alone would be lethal, violently disrupting the electron clouds of the atoms in your body, pulling your physical form apart at the subatomic level long before gravity could even finish its work. Yet, despite their invisible ferocity, magnetars are dynamic, living entities caught in a constant internal struggle between their rigid crusts and their twisting magnetic fields. The crust of a magnetar, composed of iron nuclei locked into a crystalline lattice, is subjected to immense mechanical stresses as the internal magnetic fields shift and evolve. The magnetic pressure is so powerful that it constantly tries to warp and tear the crust apart from the inside out. Periodically, the tension becomes too great for the solid lattice to withstand, resulting in a starquake, a sudden, violent fracture of the neutron star's crust, where the solid iron layers snap and shift by a fraction of a centimeter. Because of the crushing density and gravity, this tiny physical displacement releases an unimaginable cascade of stored energy, shaking the entire star and sending violent alpha waves echoing through its magnetosphere. These starquakes often trigger the most violent events in the known universe: magnetic reconnection and giant flares. When the tangled magnetic field lines become excessively twisted and stressed by the shifting crust, they snap, cross, and reconnect in a fraction of a second. This sudden rearrangement of magnetic topology releases petawatts of energy, launching catastrophic gamma-ray flares that sweep across the galaxy. A single magnetar flare can radiate more energy in 1/10 of a second than our Sun produces in 100,000 years, temporarily ionizing the upper atmosphere of planets located light years away and blinding space-based telescopes designed to monitor high-energy radiation. As we drift at a safe, astronomical distance through the quiet, velvet black of space, watching the distant silhouette of this magnetic monster, the contrast is stark and mesmerizing. Outwardly, the magnetar may appear calm and unassuming in the deep void, yet it is continuously lashed by invisible tempests of quantum energy and magnetic fury. It stands as a monument to the most extreme environments the universe can forge, reminding us that even in death, stellar remnants can harbor forces capable of tearing the very fabric of space apart, lulling us deeper into the tranquil night as the cosmic show unfolds far away. To step away from the immediate cosmic vicinity of these dead stars and travel back in time, we must relocate to the damp, quiet fields of Cambridge, England, in the autumn of 1967. It was an era when radio astronomy was still a young and pioneering science, opening up a completely new sensory window to a universe that humanity had previously only been able to see with visible light. At the Mullard Radio Astronomy Observatory, a brilliant young postgraduate student named Jocelyn Bell was meticulously analyzing miles of continuous chart paper recordings generated by a massive new radio telescope array. This custom-built telescope, constructed over 2 acres with thousands of individual dipole wires, was specifically designed to study interplanetary scintillation, the rapid twinkling of distant quasars caused by the solar wind. Day after day, week after week, Bell faced the monumental task of manually reviewing hundreds of feet of paper rolls, covered in jagged ink traces, searching for subtle anomalies buried deep beneath the thick layers of natural background noise and terrestrial interference. Amidst the endless sea of routine radiostatic, a tiny, persistent irregularity caught her trained eye. It was a strange patch of ink signals, a delicate bit of scruff that appeared on the chart paper during specific sidereal times, perfectly matching the rotation of the Earth against the distant stars. When Bell examined this curious signal more closely under higher speed chart recordings, the anomaly resolved itself into something utterly unprecedented. A series of sharp, incredibly regular radio pulses occurring at intervals of exactly 1.33 seconds. The precision of the timing was astonishing, maintaining a clockwork exactness that defied any known natural process at the time. To a human observer sitting in the quiet observation room, the rhythmic ticking sounded less like random cosmic noise and more like a deliberate, coded beacon broadcast across the interstellar void from an advanced alien civilization. Cautious, rigorous, and deeply determined to rule out any mundane explanations before raising an alarm, Bell and her thesis supervisor, Anthony Hewish, spent weeks testing every possible variable. They checked for local electrical interference from passing tractors, nearby power lines, radar signals from military installations, and internal equipment glitches within the radio telescope itself. Yet every test confirmed that the source was truly astronomical, originating from a fixed point far beyond our solar system. As they discovered a second, and then a third, and a fourth pulsing source scattered across different regions of the sky, the reality of the situation became simultaneously thrilling and unsettling. In a mixture of scientific caution and light-hearted humor, the research team temporarily catalogued the anomalous signals under the playful working designation of LGM-1, standing for Little Green Men, acknowledging the lingering possibility that they might have accidentally intercepted the first signals from intelligent extraterrestrial life. However, the idea of an alien civilization quickly lost ground as additional pulsars were discovered in completely opposite corners of the galaxy, all emitting similarly intense, perfectly timed radio bursts without any modulation or information-carrying signals that would indicate artificial communication. Nature herself was building the ultimate atomic clocks in the dark. The scientific community soon realized that these mysterious pulses were not artificial transmissions, but the long-sought observational proof of a theoretical entity proposed over 30 years earlier by astrophysicists Walter Baade and Fritz Zwicky, rotating neutron stars. The intense magnetic fields and rapid rotation rates of these dead stellar cores were acting as cosmic dynamos, sweeping narrow beams of radio emission across the galaxy like a lighthouse lamp, exactly as modern theoretical physics had predicted. The discovery of pulsars fundamentally transformed our understanding of the universe, opening an entirely new branch of astrophysics and earning Anthony Hewish the Nobel Prize in Physics in 1974, though Jocelyn Bell Burnell's exclusion from the prize remains one of the most famous oversights in the history of modern science. Yet her name remains forever linked to one of the greatest observational triumphs of the 20th century. As we reflect on that quiet laboratory in 1967, watching the historical record blend into the modern tapestry of space science, we realize that human curiosity is the true light guiding us through the dark. The discovery of these pulsing beacons did more than just confirm the existence of dead stars. It gave humanity a profound new way to measure time, map the galaxy, and drift deeper into the soothing, eternal mystery of the cosmos. Beyond their violent origins and extreme physics, neutron stars serve a deeply practical and astonishing purpose in the modern cosmos, transforming from dead remnants into the ultimate timekeepers of the universe. When we study the rhythmic pulses of millisecond pulsars over long stretches of time, we discover a stability that rivals or even surpasses the most advanced atomic clocks built by human hands in our terrestrial laboratories. While human timepieces can be affected by environmental changes, mechanical drift, or atomic decay over decades, the rotation of an ancient, isolated millisecond pulsar is anchored by the immense rotational inertia of a stellar mass packed into a city-sized sphere. Their pulse arrival times can be predicted with sub-microsecond precision across years and decades, turning these spinning dead cores into the most reliable natural chronometers known to science. This incredible precision allows astronomers to construct what is known as a pulsar timing array, turning a network of scattered neutron stars across the galaxy into a unified, galaxy-scale instrument. By monitoring dozens of millisecond pulsars simultaneously with giant radio telescopes on Earth, scientists can track the minuscule, fraction of a microsecond variations in when their pulses arrive. These tiny deviations do not happen because the pulsars are irregular, but because the fabric of space-time itself is gently stretching and compressing as invisible gravitational waves wash across our sector of the Milky Way. These rolling ripples of space-time originate from distant titanic collisions between supermassive black holes, circling each other in the dark centers of merging galaxies. By listening to the collective choir of cosmic clocks, humanity can detect the lowest frequency gravitational waves in the universe, opening an entirely new window to observe the hidden, invisible movements of space-time. Beyond listening to the universe, these reliable beacons hold the key to humanity's future expansion into deep space, offering a revolutionary method for navigation far beyond the reach of our home planet. As our spacecraft venture further away from Earth, traveling past the outer planets and out into the vast, silent ocean of interstellar space, traditional navigation systems begin to fail. The global positioning system that guides our daily lives on Earth relies on a network of artificial satellites orbiting our planet, and its signals grow infinitely weak and useless the moment you leave the immediate vicinity of our world. Even the Deep Space Network, which uses massive radio antennas on Earth to track distant probes, suffers from a severe physical limitation known as the speed of light. Because radio waves take hours to travel across the solar system, a spacecraft cannot rely on real-time instructions from mission control when it needs to make an immediate course correction or avoid an unexpected hazard in the dark. To solve this profound challenge, aerospace engineers and astrophysicists look to the stars, specifically to the steady, unyielding pulses of millisecond pulsars, to create an autonomous interstellar guidance system known as X-ray pulsar navigation. A spacecraft journeying through deep space can carry specialized X-ray detectors designed to scan the sky and measure the exact arrival times of high-energy pulses emitted by several different pulsars scattered in various directions across the galactic sphere. Just as a sailor on an ancient ocean used the stars in the night sky to calculate their latitude and longitude, or as a modern smartphone uses multiple GPS satellites to pinpoint a street address, an autonomous spacecraft can use the unique timing signatures and geometric relationships of these cosmic beacons to calculate its exact three-dimensional position anywhere in the galaxy. Furthermore, this navigation technique takes advantage of the Doppler effect to measure not just position, but velocity as well. When a spacecraft moves toward or away from a specific pulsar, the apparent frequency of its arriving pulses shifts slightly, increasing as the craft approaches the source and decreasing as it moves away. By continuously analyzing these subtle shifts across multiple pulsars, the onboard navigation computer can calculate the spacecraft's exact speed, trajectory, and direction of travel in real time. This transforms the dead star into an absolute speedometer and compass rolled into one, operating without human intervention in the deepest reaches of the cosmos. The beauty of this system lies in its complete independence from human infrastructure, ground stations, or Earth-based timekeepers. The pulsars do not require maintenance, they do not suffer from power outages, and their signals broadcast outward in all directions across the vacuum of space for free, available to anyone who knows how to listen. A probe coasting through the interstellar void could travel for centuries, far from the warmth of the sun, and still determine its exact coordinates with pinpoint accuracy, simply by measuring the rhythmic arrival of X-ray flashes from dead stars. The ancient radiation of a collapsed titan becomes the guiding light for humanity's future wanderers, ensuring they never truly lose their way in the boundless dark. As we imagine a future spacecraft gliding silently through the star-studded void, guided by the faithful ticks of these celestial clocks, the narrative of the neutron star comes full circle. Born from the violent death of a massive giant in a blinding flash of light and neutrinos, the remnant settles into an eternal, steady rhythm that outlives the civilizations that watch it. These spinning beacons bridge the gap between the chaotic fury of stellar evolution and the quiet, orderly beauty of the cosmos. They teach us how to measure time, how to navigate the trackless void, and how to find our place in the vastness of space. As we drift here in the quiet aftermath of our journey through the life, anatomy, magnetism, and utility of these extreme objects, we can let the steady, metronomic pulse of the galaxy carry us forward. The cosmos is vast, ancient, and filled with silent wonders that spin endlessly in the dark, waiting for us to understand them. We can close our eyes to the physical world, letting the rhythmic heartbeat of the universe lull us into a deep, peaceful sleep, drifting safely on the quiet currents of the night.